What's that? In the sky? Is that a plane? Hello, in this video we're going to be discussing a graphical approach to design optimization, and we are going to be optimizing the weight or reducing the mass as much as possible of a column here. We got an inner and outer radius. So let's go ahead and get started with our problem statement. Let's see. It says treating the mean radius r and wall thickness t as design variables. Solve the design problem graphically, imposing an additional constraint of r over t being less than 50. This constraint is needed to avoid local buckling of the column. Also impose member size constraints as r being between 0.01 and 1 meter, and the thickness being between 200 millimeters or 5 meters and 5 meters, right? So here we got our little diagram. We got our fixed length, and these are given to us right here as 5 meters. We got our load P, it's 50 kilonewtons. We got our modulus. We got our max allowable stress, and we have our density of our material. And here we have a mean radius diagram where we got 2r. We got our thickness being the difference between the outer and the inner radius, right? So this mean radius, for those of you who are not familiar with, in this type of configuration, it's going to be equal to the average of the outer and the inner radius. So basically, outer radius plus inner radius divided by 2. Okay, so let's go ahead and get started. The goal here is to minimize weight. Minimize weight or mass, right? So in order to do that, we have to manipulate the constraints r and t as shown here. So with, let's just say r and t. And in order to minimize the mass when we have a fixed length, and obviously in this scenario we have a fixed density and it's just fixed variables, we need to minimize our area of our cross section, right? Because the total mass is going to be equal to the area times the length times our density, right? So let's go ahead and get started with this. So area is equal to, and of a circle, let's see, of a circle is going to be pi r squared, right? So because we have an inner and an outer radius, we're gonna have area is equal to pi radius outer squared minus radius inner squared, right? But our area needs to be a function of r and t, which are our design variables here, right? So we're gonna have to convert that to this. So if we go back to here, we can recall that, in fact, we can say that 2r is equal to radius outer plus radius inner, right? That's what's given to us. Or if you want to think of it in terms of what a mean radius is, we can have r is equal to ro plus ri over 2, right? And we have our thickness. So we got thickness is equal to outer radius minus the inner radius. Now we need to get this in terms of this right here. And thankfully, these people have been very generous in setting up the problem for us. So we're going to be able to manipulate this to turn this into this rather easily. So let's go ahead and just multiply these two together just to show you guys what we get. We got Ri, right? And we got Ro minus Ri. So let's do some multiplication there. We got Ro squared. We got minus Ro, Ri. Got that right there. We got plus Ri, Ro, right? Minus Ri squared. So we cancel this, cancel this, and lo and behold, we're left with this right here. So in order to simplify this into this, we can say that area is equal to pi times RT times 2, right? Because that's what we have here. So with that, we can start optimizing. So if you guys will recall from the problem statement, one of the variables that we're given is our maximum allowable stress. So we're going to go ahead and get started with this. As we know, stress is equal to force over area, and we just solved for our area here. So we're going to have 250 times 10 to the 6 pascals there. It's going to be less than or equal to our load, which was also given to us, over pi r times 2 times our thickness, right? And that's what we solved for here. Okay, and with that, let's go ahead and simplify this a little bit more. Let's say 250 times 10 to the 6 minus, and we have our 50 kilonewton load, so 2 pi RT is less than or equal to 0, right? And that's going to be our first equation that we will be graphing, and we'll be doing that later. If you recall, one of the constraints here was saying R over T must be less than 50. Let's go ahead and write that down. R over T is less than or equal to 50. And that's going to be our other constraint that we'll be graphing. We also got some geometrical constraints as well for the mean radius and for the thickness. So let's go ahead and just jot those down while we're at it. So we got 0.01 meters R. So that's going to be our third equation. And we got T. Oh, whoops, we got that backwards there. Let's go ahead and ixnay that. We got RT must be less than or equal to 5 meters. And it must be greater than or equal to 200 millimeters or 0.2 meters in this case. So that's what we're going to go with right there. And now we also need to take into account the critical load. So here we're given the load of 50 kilonewtons, so that's what we're going to be using. And I am actually going to be taking an equation from my college handbook of the critical load for a column, which is as follows. Oh, that's 16 L squared. Oh, this would actually be inner and outer radius, not mean inner or outer radius, which we don't have in this problem. It's kind of confusing. Okay, so that's that. And in order to keep this video from turning into an algebra video, I'm just going to go ahead and give you what that simplifies to down in mean radius and thickness, as the objective here is to instruct just the concept of turning it into the variables as they are our design variables. So that simplifies to pi cubed E, and again this is a constant given to us. We got our R cubed over 4 L squared, right? And we need this to be less than or equal to our 50 kilonewton force. Right? So that's going to be our fifth equation that we'll be plugging into our graphing calculator there. You can manipulate this whichever way you want, depending on how friendly your calculator is, but this is sufficient for me. We just have to recall that this is a fixed number. So that right there is going to be 210 times 10 to the 9th newtons per meter squared. We need to make sure that we maintain our similarity in our units, or else it'll throw a whole system out of whack here. And this right here is also a fixed value of 5 meters. So it's going to be 5 meters, right? And with that, we can go ahead and get started with graphing. So here we have our Desmos graphing calculator, and I have plugged in our equations into the sidebar here. So let's go ahead and see what they look like. Got our first equation. So this is going to be our working area. So our values for thickness and radius have to lie within this range. And just for reference for you guys, in this scenario we have the x and the y axis. In the x-axis we have the thickness, and in the y-axis we have plotted the median radius. Right, so we got our other value right there, looking good. We got our minimum and maximum values supplied to us as constraints. So as you can see, we go from 1 to 0.1 right there, or 0.01. We got our thickness, which must be between 200 millimeters and 5 meters. So that is displayed there. We have our final equation that we used, which is our critical load calculator. My bad, our critical load. And this is what we have here. And since this right here, we can turn off because it's not really adding value once we are familiar with the fact that it encompasses the entirety of this other area over here, which is what we're going to have to be working with. So just in order to remove some confusion, let's go ahead and remove that. We have to keep these right here. So this is kind of helps us, gives us a little guide right there. Okay, so we got to be in that range. And let's turn that off really fast and just see what we're working with. So if we did our analysis correctly, that would indicate that our minimum would be right here. And this is the values that we would choose for the median radius, mean radius, sorry, and thickness. So that's how we do that. As always, thank you guys for watching. If you have any questions or concerns, please drop a comment down below. If you think that I did something wrong or incorrect or would prefer some clarifying, please let me know, and I will adjust the video accordingly, or upload a new video, and whatever is fit. As always, thank you guys for watching.